Good morning, students. So in our last class, we discussed about the adjoint of a matrix, is not it? And there we discussed how to find out the 3 by 3 matrix as well as 2 by 3 matrix. So there also we discussed the cofactor and minor, because in adjoint already we know how to find out the minor and cofactor, because these two are needed there. So now after that, what you have to do, here one theorem is there, theorem number, just you have to write as a theorem, and the theorem is what here, if you see A into adjoint of A. So adjoint of A means if a matrix given to us, so easily we can find out the adjoint there. So that means here A is a, we consider as a matrix. Is it clear? Of any order. It may be 2 by 2, it may be 3 by 3, or it may be n order. So here A into adjoint of A, if we multiply this two, this result always same with adjoint of A into A. If we multiply these two, then the results are same. These two results are always same according to the theorem, and this result is equal with determinant of A into I. This I means the identity matrix. Identity matrix is totally depending on the matrix A. If A is 3 by 3 matrix, then here we have to consider I as an order 3 matrix. Is it clear? So this one is identity matrix. So this theorem is very important, and this theorem we need later on. A into adjoint of A, if we multiply these two results, then this result is always equal with adjoint of A into A, and this result is equal with determinant of A into I. Is it clear? Okay, now after that, next another theorem you see here. Actually this one is as a note also you can write theorem. Suppose if we consider a matrix A, and this matrix A is a matrix here, this one is a matrix here, and this matrix, if we find out the determinant of this matrix now, so for each and every matrix easily we can find out the determinant. And determinant, how can we find out? All of you know how to evaluate this one. So if we find out the determinant of the given matrix, and if this value is equal to 0, remember first a matrix given to us, and if we find out the determinant, and if the determinant value is equal to 0, then it is known as singular matrix. Then it is known as what? Singular matrix. Is it clear? Secondly, the second one you see here, if A is a matrix given to us, and again if we find out the determinant of A, and if this determinant of A value is not equal to 0, then it is known as non-singular matrix. Then it is known as non-singular matrix. Is it clear? All of you understood the difference between these two? If the determinant value is equal to 0, then it is singular, and if determinant of value is not equal to 0, then it is known as non-singular matrix. Is it clear? So after that, so another theorem is here. This theorem is, if A and B are two non-singular matrix, if these two are non-singular, that means their determinant value is not equal to 0. If A and B are two non-singular matrix, then their product is also non-singular, AB and BA. So these two are also non-singular. I repeat this one, if A and B are non-singular, if A and B are non-singular means what? Determinant of A is not equal to 0, as well as determinant of B is also not equal to 0. So if these two are non-singular, then their product is also non-singular matrix. Is it clear? Okay. Now the next theorem, if you see here, this one is, in this case what we get, see carefully. If suppose two matrices are given, here, and these two are the matrix, and now here if we find out the product of these two matrices, remember first of all two matrices are given, and what you have to do, we have to find out the product of these two matrices, and after finding the product here, we have to find out the determinant of this matrix. After product of these two AB, now we have to find out the determinant of this matrix, and after evaluating this one, obviously we get some result, and this result is always equal with individually, if we find out the determinant of A as well as the determinant of B individually if we find out separately, and after that if we multiply whatever the result we get after multiplying, and if we find out the determinant, these two results are always we get same. Is it clear? First of all, we consider two matrix, non-singular matrix A and B, and then we have to multiply these two, and then we get, suppose the multiplication is AB, and if we take the determinant, then obviously here we get some value, isn't it? We keep this one, and now individually we have to find out the determinant of A as well as we have to find out the determinant of B, and after finding the determinant of A and B, we have to multiply these two. If we multiply these two, the result will be same as AB, determinant of AB. Here or here result duita ki hobo? Same hobo. So this one is the theorem number, I think 3, 4, 5. You write here. So this one is AB, multiplication AB, and then here we get determinant of AB equal to determinant of A into determinant of B. So now in this case, why we discuss this one? Because in this theorem we have to apply this result. So you see how can we apply determinant of AB. So in place of determinant of AB, also we can write determinant of A into determinant of B. Isn't it? We can write or not? So now here, from these two, if we take any two result, and after that if we take the determinant, then easily in this way we can separate the result. Let's say here, how can we solve this one? So already we know this result. So which one is A into adjoint of A? A into adjoint of A equal to, this one we write adjoint of A into A equals to, this result is equal to determinant of A into I. I is what? An identity matrix. Suppose here we consider the matrix A is of order 3. Suppose we consider this one is order 3 matrix. So if A is a order 3 matrix, so obviously here the identity matrix also we consider of order 3, isn't it? So now here, suppose if we take these two now, so A into adjoint of A equals to, if we take this one, determinant of A into I3. Why we write I3? Because A we consider as an order 3, so that's why order 3 identity matrix we have to consider. So now this A into identity of this one 3, this one also we can write A into I. Identity of 3 means here I3 means 1 0 0 0 1 0 0 0 1. This one is the identity matrix, isn't it? So this one is the identity matrix, here we write. And now here in case of matrix, we know with each and every element we have to multiply. So that's why here if you multiply this one, then first one we write determinant of A 0 0 0 0. This one we write determinant of A, and then finally here we have to write this one is 0 0. Sorry, this one is here not. This one we write determinant of A 0, and then finally we write here, this one is determinant of A 0. Clear? This one is the 3 by 3 matrix, and in the left hand side this one we get here adjoint of A. This one we get. Now after getting this one, now if we take the determinant on both sides, of these two matrix, then what you have to write? The left hand side we have to write determinant of A into adjoint of A equals to, this one we write the left hand side, as well as in the right hand side what you have to write? This one you have to write determinant of, this one is determinant of A 0 0, second one is 0, determinant of A 0, and this one is 0 0, this one you have to write determinant of A. Is it clear? Now in this case, if you see, very interesting this one, since already we know determinant of AB equals to what? Determinant of A into determinant of B. So that's why in this case what you have to write? Determinant of A into determinant of adjoint of A, we can write like in this way. Is it clear? Because already we discussed this one. So now in this case, when you have to take common, so in case of determinant, from each row or each column we have to take common, isn't it? So that's why from the first row if we take common, one determinant A come, so from the second another one, and from the third another one. So total how many are come here? 3. So that's why we have to write here determinant of A cube, and this one ultimately remain here 1 0 0 0 1 0 0 0 1. Is it clear? This one remain here. So now if we evaluate this one, so determinant of A into this one, we write adjoint of A equals to this one, we write determinant of A cube, because if we evaluate this one, the value we get 1 here, isn't it? So now here already one determinant of A is there, so this one ultimately we can write in this way, A into adjoint of A equals to this one, we can write determinant of A cube minus 1, determinant of A whole cube. So if we shift this one, then this one either you can cancel or you can write 3 minus 1. So why we write actually in this way? If the order is 3, then we get adjoint of A equals to what we get? Determinant of A to the power 3 minus 1. If the order is 3, then we write 3 minus 1. If the order is 5, then we write 5 minus 1. And if the order is n, suppose order given, if the order is given n, then what you have to write? In this case, we have to write adjoint of A. So adjoint of A equal to this one, we write here determinant of A to the power n minus 1. So this one is the general formula. And this formula we have to remember. Adjoint of A equal to what? Determinant of A to the power n minus 1. N is what? The order of the matrix. So if order n given, then we have to apply this formula. So in exam, if the question is given here, if order is 5, find out the determinant of adjoint of A. So we directly write down the answer like in this way, determinant of A to the power 5 minus 1. Sometimes the questions are given like in this way, not only adjoint of A, sometimes this result also we have to find out. Determinant of A into adjoint of A, we have to find out. So in this case, only we have to write determinant of A to the power 3. And if we want only adjoint of A, then we have to write determinant of A to the power n minus 1. So I hope all of you understood this one. So that's all for today. So in our next class, we discuss the inverse. How can we find out the inverse of a matrix? Is it clear? Okay.